Hello everyone. Today I will finish talking about chapter 1 chemical formula and moles for IG level A. I'll be talking about balancing chemical equations, solution and the concentration. I will also be talking about gas volumes and stoichiometry. I will provide a link to download the material, and also I provide a link for the website channel. Let's start by talking about balancing equations. For any chemical reaction, it's a process in which a substance or substances is changed into one or more new substances. Chemists present these changes into chemical equations and using symbols. So I have here on this left hand side I have the reactants, and the right hand side contains the products. For the number that is written on the left hand side of any symbol, it is the stoichiometry of the reaction that indicates the number of moles involved in the reaction. So if I wanted to balance this chemical equation, I could see here that I have 3 carbons and 8 hydrogens, plus I have 2 oxygens, and the number of carbon inside side is only carbon atom and 3 oxygens, because I have here 1 and I have here 2, so I have 3 oxygens and I have 2 hydrogens. So to be able to make this part equivalent to this part, if I multiply this the carbon dioxide by 3, I may have the same 3 carbon atoms. So first step would be multiplying here by 3. So if I multiply this part by 3, I will have C3H8 plus O2 to give me 3CO2 plus H2O. Now looking again at the number of carbons, so I have here 3 carbon atoms and I have here 3 carbon atoms, but now I don't have the same number of hydrogens. So I'm avoiding looking at oxygen because it appeared more than 1 on that side, but for hydrogen it appeared only once, and for the carbon it appeared also once. So my first step would be looking at the compound, at the elements that appeared only once on that side and only once on that side. My second step would be trying to balance this element, then go from that point to balance the more complicated element which appeared more than 1 time on each side. So for here, if I wanted to also to balance the hydrogen, so I need here to multiply this part by 4. So my third step would be multiplying this part by 4. So I still have the 3CO2 plus 4 H2O. This means I have here 3 carbons and 8 hydrogens, and I have here 2 oxygens, while here I have 3 carbons plus I have here I have 6. So usually I multiply the number on the left with the subscript number, so 3 by 2 is equals 6, and here I have 4, so 6 and 4 is equal 10 oxygens, and I have 8 hydrogens. So if I have, I could see that I already balanced the carbon atoms and the hydrogen atoms. I'm left now with balancing only the oxygen. So if I have here 10 oxygens and have here 2 oxygens, if I multiply this symbol by 5, I can balance my equation. So I will multiply this oxygen by 5. So C3H8 plus 5O2 to give me 3CO2 plus 4 H2O. Now my final step would be calculating the number of atoms on each side and verifying if I correctly balanced my equation or not. So I have 3 carbons and I have 8 hydrogens and I have 10 oxygens, because 5 by 2, and here I have 3 carbons plus I have here 6 oxygens, and I have here 4 oxygens, which mean 10 oxygens, and I have here 4 by 2 is equal 8 hydrogens. Now if I looked at both sides, I can see that they are equivalent. This is my final form for my balanced chemical equation. Balancing chemical equation steps, usually I have to follow certain steps to be able to balance my chemical equation in a correct way. First, I have to identify all the reactants and products and write them correctly on each side of the equation. So I start by writing the reactants on that side and the products on that side. Then I start by balancing the equation and trying different coefficients to make the number of atoms of each element the same on both sides of the equation. So if I look here, I have 2 oxygens and I have here 1 oxygen. So I try multiplying by a coefficient, which was here in that case 2, to be able to have the same number of atoms on that side, which is 2 oxygen, equivalent to that side, which is 2 oxygen. Then I further move to balance the other elements. Usually I look at the element that appeared only once on that side and only once on that side. Then I move from that to the elements that appeared more than once. For that equations, actually both of them, the oxygen and the hydrogen, appeared only once here and only once here. But in the previous example, I had the carbon and the hydrogen appeared only once here and only once here. But the oxygen, I delayed balancing the oxygen because it appeared here only once, but on that side it appeared twice. My last step, my final step, should be checking my balanced equation and make sure that I have the same total number of atoms on each side of the equation. Let's take an example. Balance chemical equation for the reaction of iron with hydrochloric acid to form iron chloride, FeCl2, and the hydrogen. So I have here iron that reacts with hydrochloric. So this is the reactants, and on that side I have iron chloride and hydrogen, which are the products. So if I counted the number of atoms, I have 1 iron and I have 1 hydrogen and I have 1 chlorine. But on that side I have 1 iron and 2 chlorine atoms, and I have here 2 hydrogen atoms. This means I have to multiply this part by 2. So if I started multiplying this part by 2, I have to remember to multiply the 2 by the H, the hydrogen atoms, and I have to multiply it by the chlorine atoms as well. So I have Fe plus 2HCl to give me FeCl2 plus H2. Now if I try to count the number of atoms, I have 1 iron atom, I have 2 hydrogen atoms, plus I have 2 chlorine atoms. Here I have 1 iron atom, and I have 2 chlorine atoms, and I have 2 hydrogen atoms. So this means I checked my my equation, and now it is completely balanced. So this is the last form of the balanced chemical equation. Write balanced equations including state symbols for the following reaction. An aqueous solution of zinc sulfate reacts with aqueous solution of sodium hydroxide as the products are precipitate of zinc hydroxide and aqueous solution of sodium sulfate. So first I have to write my equation. I have zinc sulfate, and it says here that it is an aqueous solution, so I write AQ, plus I have here also an aqueous solution, this time sodium hydroxide NaOH, and the product is precipitate zinc hydroxide, so I have zinc hydroxide, which is precipitate, so I have here S, plus aqueous solution of sodium sulfate Na2SO4, and this is an aqueous solution. My second step will be counting the number of atoms on both sides. So I have here one zinc atom, and the sulfate. If I kept the sulfate formula together instead of just counting the number of oxygen, it will be easier for me because there is no dissociation for any groups of those, the hydroxyl group or the sulfate group. So I have one sulfate group, and I have one sodium atom and one hydroxyl group. Here I have one zinc atom and I have 2 hydroxyl group, and here I have 2 sodium atoms, and I have here 1 sulfate group. I could see the sulfate are the same on both sides, and the zinc is equal on both sides, and for only the sodium and the hydroxide on that side is not equal to that side. If I looked here, I could see it is written here 2 and 2, so if I multiplied my formula here by 2, I'll be able to balance my chemical equation. So zinc is O4 aqueous plus 2 NaOH, and this is also aqueous solution, to give me zinc hydroxide, which is solid, and Na2SO4, which is an aqueous solution. Now if I count the number of atoms, I have 1 zinc on both sides, I have 1 sulfate on both sides, I have 2 sodium and 2 hydroxyl, and I have here 2 hydroxyl and 2 sodium. So this is the final stage, the balanced chemical equation. Now moving to balancing ionic equations. For ionic compounds dissolved in water, they usually dissociate or separate into ions. Chemists prefer to write ionic equation for precipitation reaction. If I looked here, I have sodium NaCl, and water aqueous here mean it reacts with water, it dissociates in water. It usually give sodium ions and chlorine ions. Now let's look at an example. If I tried here to look to find out what is my balanced ionic equation for zinc reacting with copper sulfate to give me zinc sulfate and the copper. So first I need to write down the ionic formula of the equation. So usually the copper would dissociate into copper ions and sulfate ions, which is equal to negative. This is an aqueous solution to give me zinc, which is in that case would be so here is a solid, so I keep it as it is, but here because it is an aqueous solution, it will dissociate into 2 ions, the zinc ions and the sulfate ions. So zinc will carry the 2 positive charges, and the sulfate will remain with its 2 negative charges. This is an aqueous solution plus the copper, which is in a solid state, so I don't write any ions. Now my second step would be cancelling the part of the ions that appeared on each part of the equation. I could see here that sulfate appeared in that side and appeared on that side, so I will cancel the sulfate, and now I need to write down the final form of the ionic equation. So zinc in solid state plus copper. I have to remember to write the ions to give me zinc ions plus copper, which is solid. So this is my final form of the balanced ionic equation. Let's take another example. Write ionic equation for the reaction of bromine with potassium iodide, and to give me potassium bromine and potassium bromide and iodine. It's already a balanced chemical equation. If I try to write my ionic equation, I will not change the bromine, but I will write down the dissociated form of this part, which is potassium is dissociated, potassium iodide is dissociated into potassium ions and iodide ions. This carries 1 negative charge, and that one carries positive charge. And on that part, the potassium also carries positive charge, and the bromine carries negative charge. This is an aqueous state plus iodine. Now if I try to cancel the part that appeared on both sides of the equation, it will be the potassium ions. So I write my final form of my equation plus 2 iodide ions to give me 2 bromide ions plus iodine. Let's take another example. Write a ionic equation for this precipitation reaction, the reaction of copper sulfate with sodium hydroxide to give me copper hydroxide and sodium sulfate. First, I have to look if my I have a balanced equation. So I have here 1 copper and I have here 1 copper. I have here 1 sulfate and I have here 1 sulfate. As for the sodium, I have here 2 sodium and I have here 2 sodium, and here I have 2 hydroxide groups and I have here 2 hydroxide groups. Now let's write the dissociated form or the ionic form of the equation. The copper will carry 2 positive charge and the sulfate will carry 2 negative charge. I have to keep the aqueous solution, and 2 Na. This will dissociate into sodium ions and the hydroxide ions. Nothing will happen to this part because it's a solid, and that part will dissociate as well. So I have here 2 sodium ions and 2 sulfate, 1 sulfate ions, which carries -2. I will cancel now the parts that appeared on both sides of the equation. I have here sulfate appeared on that side and that side. The sodium appeared on that side and that side. I will cancel them. Now I have the copper, which in that part, which is an ions, and here the sulfate, the hydroxide. To give me copper sulfate, copper hydroxide, which is a solid state. So this is my final ionic equation. Now moving to solution and concentration. I can calculate a concentration of a solution. The concentration of a solution is the amount of solute dissolved in solvent. So if I know how much solute do I have and how much solvent do I have, I can calculate my concentration. So my concentration unit is mole decimeter, cubic decimeter, and that would be equal to the number of moles of solute in moles divided by the volume of solution in cubic decimeter or in liter. So we can say that the number of moles, so if I wanted the number of moles, I can multiply the concentration by the volume of the solution. That is in case if I know the mass, I can even further convert the mass into moles, and from moles I can calculate the concentration. Let's take an example. Calculate the concentration in mole cubic decimeter of the following solution. A solution of sodium hydroxide, NaOH, containing 2 grams of sodium hydroxide in 50 cubic centimeter of solution. So now I have the volume, and I have the grams, which means I have the mass. So my first step would be converting the mass into moles, and I will use this moles to get the concentration. So first step, grams, moles of NaOH would be equal to, if I have 2 grams of NaOH, if I know that 1 mole of NaOH contains 40 grams of NaOH. So how many moles do I have? So in that case I will have 0.05 mole. Now I have the number of moles, so I can get my first I have to remember to convert the decimeter into the centimeter into cubic decimeter. So to be able to do that, I have centimeter cubic to decimeter cubic. I would divide the 50, which I have here, by 1000, and the answer to that would be 0.05 as well. in decimeter, cubic decimeter. So the concentration of NaOH would be equal to 0.05, the number of moles, divided by the volume, 0.05, in here in decimeter, cubic decimeter, to be equal to 1 mole per cubic decimeter. Now let's look at another example. Calculate the mass of anhydrous copper sulfate in 55 cubic centimeter of 0.2 mole decimeter minus 3 solution of copper sulfate. Now I need the mass, and I have the volume, and I have the concentration. If I wanted to do it in one step calculation like I showed you before, so I need the mass of copper sulfate in grams. To be able to do that, I need first to calculate the molar mass of copper sulfate, which would be equal to, for the copper it's 63.5 plus 32.1 for the sulfur, and I have here 4 oxygen atoms, 4 multiplied by 16, and that would be equal to 159.6 grams. So this is my molar mass. In that case, I will use that to obtain my the mass of copper sulfate. So I will start by writing down my concentration. I have to write down the units, so if I end up with the right unit with a conversion, this means my calculation is correct. Now I write down my centimeter cubic, knowing that I need to convert it to decimeter, cubic decimeter. I know that each 1 cubic decimeter is equivalent to 1000 cubic centimeter multiplied by, now I obtained from that step I would obtain the number of moles, and from the number of moles in that step I have to convert it into grams. If I know that the molar mass of copper sulfate this is in grams for each 1 mole, if I calculated that, it would be equal to 17556, which is two significant number is 1.8 grams. So again, if I need to calculate the mass, first I need to use the information I have, which is the concentration and the volume, to give me the number of moles. And from the number of moles, I can convert it into grams by multiplying by the molar mass of copper sulfate. Calculating solution concentration by titration. I use titration experiment to obtain my concentration. Usually I have a period which I fill it with the titrant, with a known concentration of the titrant, and a titration flask. This titration flask contains a certain amount or certain volume of my titrated sample that I want to find out the concentration of this sample. And also I use indicator to give me to indicate me to the end point. Usually change of color. The change of the color would give me indication for the end point of the reaction. I use this period to drop a certain volume from the period. So I have to know here the volume I driven in the flask, and I have to know the volume of the for the titrated sample, unknown sample concentration in the flask. Example: 20 cubic centimeter of 0.04 mole per cubic decimeter solution of sodium hydroxide was exactly neutralized against 25.25 cubic centimeter sulfuric acid. Calculate the concentration of the sulfuric acid. If I looked here at the equation, I have to look first if my equation is balanced. So this is a balanced chemical equation, but usually you have to check before starting your calculation if your equation is balanced or not. My second step will identifying the given information. So here I have the volume and I have the concentration of the sodium hydroxide. And it is neutralized against a certain volume of sulfuric acid, so I know the volume of sulfuric acid. Now I need to know the concentration of this sulfuric acid. First, I need to know the number of moles of NaOH that reacted, that is used in this reaction. To be able to know that, I have to multiply the volume by the concentration. So I multiply 0.4 by the 20, and I have to remember that I need to convert the cubic centimeter into cubic decimeter. So each one cubic decimeter is equal to 1000 cubic centimeter. So the answer to that would be equal 0.008 moles. If I know that for each 1 mole of sulfuric acid, it reacts with 2 moles of NaOH. Now I need to know how much moles is used in that is reacting in case if I have NaOH, the number of moles of NaOH is equal to 0.008. So the number of H2SO4 moles would be equal to 0.008 moles NaOH multiplied by 2 multiplied by 1 and divided by 2. This will be equal to 0.004 moles. The last step would be calculating the concentration of H2SO4. So the concentration will be equal to the number of moles divided by the volume, and I have to remember to convert my volume. So 0.004 moles divided by 25.25 cubic centimeter multiplied by 1000 cubic centimeter divided by 1 cubic decimeter, and this will be equal to 0.317 mole per cubic decimeter. Now, deducing the stoichiometry by titration. From titration, we can get the number of moles of the reactants, and from which we can deduce the stoichiometry. Deducing stoichiometry by titration. Let's now think what sort of information I can gather using titration. So in titration, usually I can, if I have A titrating, I'm titrating A against B. Usually I know my volume of A because it is inside the burette, and I know the concentration of this A. And I'm titrating against B where I know the volume of B, but I need to figure out the volume of C. So I can use my information about A to find out the number of moles of A. So from that, my number of moles would be equal to the volume by the concentration. And from knowing the number of moles, I can find out how many moles is reacting against B. So I can figure out the number of moles of B, and from knowing the number of moles of B, I can use the same relation to find out the C. So in here of B, so I use the number of moles of B, which I already know, to find out the concentration, which is C. So in that case, C would be equal to moles of B divided by the volume of B. If I know my AA volume and concentration, and I know B volume and concentration, I can know how many moles reacted of A reacted with how many moles reacted with B. So here in that case I will find out the number of moles, and here I will find out the number of moles by multiplying the volume by concentration in both cases, and the ratio between the number of moles of A against the number of moles of B can give me the stoichiometry of this reaction. Let's take an example. If I have 20 cubic decimeter of metal hydroxide of a concentration 0.06 moles per cubic decimeter was titrated against 0.1 mole per cubic decimeter hydrochloric acid, it requires 24 cubic centimeter of the hydrochloric acid to exactly neutralize the metal hydroxide. First, calculate the number of moles of the metal hydroxide. Second, calculate the number of moles of hydrochloric acid. The third part wants me to calculate write down the simplest ratio, mole ratio of the metal hydroxide against the hydrochloric acid, and I need to also write a balanced chemical equation for this reaction. If I looked here at the given information, I have 20 cubic centimeter of the metal, so I know the volume of the metal and I know its concentration, and I also know the concentration of the hydrochloric acid and the volume of the hydrochloric acid. So my first step would be calculating the number of moles for metal hydroxide. For that, I will multiply the concentration by the volume. So I will multiply the 20 by the 0.06. So I multiply my 20 I have to use the conversion factor here. So I know that 1 cubic decimeter is equivalent to 1000 cubic centimeter, and I multiply here by 0.06 my concentration. This will be equal to 0.0012 moles. So now I know my the concentration of my metal hydroxide. Now I need to calculate the number of moles of my HCl. This will be equal to, I know that from here I know I have this concentration and I have this volume, so I have 0.1 and then I will multiply it by the volume, which is 20, and I will multiply also by the conversion factor 1. Decimeter is equivalent to 1000 cubic centimeter, and this will be equal 0.0024 moles. So if I write the ratio of the acid against the ratio of the hydroxide, I will write it here 0.0012 against 0.0024. If I divide it here by the smallest number 0.0012 and divide it here by the same number 0.12, this will be equal to 1. This will be equal to 2, and this will be equal to 1. This means the ratio between the acid and the hydroxide is 2 to 1. So each 2 moles of the acid will be consumed against 1 mole of the hydroxide. So if I wanted to write the balanced chemical equation, I will write 2 moles for the HCl plus, I will put the symbol M for the hydroxide and the MOH to give me H2O plus MCl. I have to remember here that I have 2 Cl, 2 chlorine atoms. This means my metal is actually divalent metal. So if it is divalent, I have to write here also 2. calculating involving gas volumes. Now, if I have gases instead of solutions that is reacting in a chemical equation, I can use the molar gas volumes to find out the ratio of my reactants and the products. So for Avogadro's hypothesis, at a certain temperature and the pressure, all volumes contain the same number of molecules. So at room temperature and the pressure, 1 mole of a gas has a volume of 24 cubic decimeter at temperature 20 degrees centigrade and pressure 1 atmosphere. Let's take an example. Calculate the volume in cubic decimeter occupied by 26.4 grams of carbon dioxide. So here I'm giving the mass and I'm giving that it is at room temperature. If it is at room temperature, this means each 1 mole, the volume of 1 mole is equal to 24 cubic decimeter. So first I need to convert the mass into moles, and from that I can convert the number of moles I'm giving into the volume by using this conversion factor. First I need to know the molar mass of carbon dioxide. So if I calculate the number of moles of carbon dioxide, it's equal to 12 plus 2 multiplied by 16, and this will be equal to 44 grams. Now if I wanted to find out my volume, will be equal to the number of grams that I'm giving, 26.4 grams. If I know that each 1 mole contains 44 grams of carbon dioxide, and from that I obtain the moles, and if I know that each 24 cubic decimeter is considered to contain 1 mole of carbon dioxide, this will be equal to 14.4 cubic decimeter. Let's verify if we calculated in right, if our calculation is correct. So I cancel the grams with the grams and the moles with moles. I end up with the cubic decimeter. So I have to remember, if I'm giving the mass, I have to convert this mass into moles, and I will use the relation that if each 1 mole contains 24 cubic decimeter volume, I can obtain my the volume for this amount, which is 26.4 grams. Another example, a flask of volume 120 cubic decimeter is filled with helium gas at room temperature. Calculate the mass of helium present in the flask. Here I'm giving the volume and I'm asked to get the mass. So I can use the volume because I know that is at room temperature. I can find out how much volume of is equivalent to how much moles. So I can calculate the number of moles, and from the number of moles I can convert it into the mass. In one step I can write down that the mass of helium would be equal to the unit I'm giving, which is 120 cubic decimeter, and I need first step to convert my my cubic centimeter into cubic decimeter. So if I know 1 cubic decimeter is equivalent to 1000 cubic centimeter, the second step, now I get from this step the decimeters. If I know that each 1 mole contains 24 cubic decimeter volume of helium, and if I know that helium itself have atomic mass of 4, each 1 mole contains 4 grams of helium. This means the number of grams is equal 0.2 grams. So I could see here my first step is converting the centimeter into decimeter, cubic decimeter, and then I will use the conversion not the conversion factor, but the relation between the moles and the volume to get the number of moles. And from the number of moles I can convert it using the conversion factor into mass of helium in just one single step. And if I cancelled the my units, I could find that I end up with the desired unit. So it's easier for me if I used one single step to minimize my error. So the gas volume stoichiometry. Now if I know the volume of the gases in a reaction, we can deduce the moles, and from the moles we can know the stoichiometry of a reaction. Or we just can use the volumes ratio to correlate the stoichiometry, which is easier for us. Let's take an example. 50 cubic decimeter of gaseous hydride of phosphorus BHN reacts with exactly 150 cubic centimeter of chlorine to form liquid phosphorus trichloride and 150 of hydrogen chloride gas. How many moles of chlorine reacts with 1 mole of gaseous hydride? And deduce the formula of the phosphorus hydride and write balanced chemical equation. So I can use the volumes ratio, the ratio between the volumes, to get my stoichiometry and write the balanced chemical equation. Let's write first the equation. BHN reacts with chlorine gas Cl2 to give me BCl3 plus HCl. I'm giving here the volume, which is equal to 50, and here 150 cubic centimeter, and here 150 cubic centimeter. I don't have to convert my cubic centimeter into cubic decimeter because I'm just using a ratio. So if I divide it here by the smallest number, which is 50, I will get the ratio between the three of them, 1 to 3 and 3. Now let's try to write down the chemical equation. So BHN plus 3Cl2 to give me BCl3 plus 3HCl. If I try to balance this chemical equation, I will find out that I need in this part 3 hydrogens. So this means I have my B is actually BH3 plus 3Cl2 to give me BCl3 plus 3HCl. If I look again, I have here 3 hydrogens and here 3 hydrogen. I have here 3 chlorine atoms, and I have here 3 and 3 chlorine atoms and 1 phosphorus on both sides. So this is my final balanced chemical equation. By that we ended the first chapter. See you next video with chapter 2, atomic structure. Thank you and goodbye.